Okay, let's get started. So, are there any questions? What's in a week from today? Test. I'll ask again. Are there any questions?
It's going to be
So, good question. More of you should ask questions like that. So his question was, is the test cumulative? So yes and no. So yes, in the sense that in order to know what a context-free language is, you need to know what a language and a regular language is. But do you think I'm going to ask something specifically about the regular languages? No, probably not. So it's going to ask specifically things past the regular languages, but you may need to know things about regular languages to be able to use them. Does that make sense? Okay. Any other questions about the test? Or anything else, really? So on the course website, I posted a whole bunch of new stuff. Midterm 2 from 2 years ago, so that should be something similar to what you will expect, but of course longer because they had shorter tests, but the same stuff. For what the test is going to cover, I am not sure yet. Everything that we did in Chapter 2 that we did in class, that will be on the test for sure, but it's just I don't know whether Turing machines, which we're going to get to, are going to be on there or not. Depends on how far we get. I probably am going to include only some things about Turing machines, maybe not all, but we'll see how we go. But definitely Chapter 2, absolutely for sure. Any other questions?
Anything with the final exam that's final?
Oh, great point. So I forgot to say this. I posted this on Piazza that a while ago we made that poll where we had the choice of what to do with the final exam, either to have it entirely on the 10th of July or half and half, half on the 10th and the other half on the 11th. So there was a majority of people who said to have the entire thing on the 10th and have no class on the 11th. So that's what we're going to do. And I reflected that on the course website by putting it in bold, underline, and italics. So it's the final exam is not on July 11th. It's not on July 11th. No one will be here on July 11th. It's entirely on the 10th of July. Same class time, everything, but the 10th of July. What day is the final exam? The 10th. Is it on the 11th of July? I'm going to say this every single class until then, and I hope you keep saying the 10th of July, okay? So it's on the 10th of July, okay. Other questions? Okay, so last time what were we starting to talk about? The Turing machines. So we had this Turing machine model. So what is a characteristic about a Turing machine that wasn't characteristic of like a PDA or a DFA or whatever? Yeah, it had this tape thing. So it's this one-way infinite tape thing where we put the input right on the tape, and then afterward we have an infinite set of blanks that appear after the input. So what else is characteristic about a Turing machine that, say, a PDA doesn't have? What can we do on a tape that we can't do on a stack? Yeah, move left and right. So we have this pointer, this tape head thing, that can move left and right across the tape. And what else could happen here? Well, what else could happen? Is the input going to stay exactly 0, 1, 0, 0 here? Or what could happen? Yeah, I could write something. So I could, for example, when I'm looking at this 1 here, I can say, oh, if I see a 1 at this particular moment, I'm going to write a different character, say X, and then maybe move left in this case. So after this transition occurs, the head's not going to be pointed here, but is now going to be pointed 1 space to the left, 1 cell to the left, because the transition said, if you're at this particular point and you see a 1 here, write an X there and move the tape head left. Okay? So that was what we saw in the transition function. We saw that if we're in a state and we're reading an input symbol here, then we're obviously going to change state, but we're going to write some symbol there, so it may be not necessarily the same symbol, and then furthermore, we're going to specify the tape head can either move left or right, in 1 position every single time. Okay, any questions about the model that we introduced last time? Okay, go ahead.
Can you get stuck in that?
Like,
If you see a 0, you replace it with a 0. You see a 0, so you replace it with a 0.
Good point. So if we say, okay, like we're looking at a 0 right now, and we say, oh, write a 0 at this point, the key here is that we can't stay at the exact same cell. We have to move left or right. But that raises a good point. What if we were instead, not at these points, but let's just say we were right here, and our instructions say, whatever state we're in, write a 0 because we see a 0 and move right and go to this other state. And this other state says, when we go over to here, when we see a 0, write a 0 and move left. So we could have this infinite behavior that happens here. And we'll address that when we talk about computation. So Turing machines actually can run forever, whereas a DFA can't. Can a PDA run forever? Yes. But here's something interesting that I want you to think about. You won't have to worry about it for a test or proving it, but it's just a nice insight. Consider a grammar in Chomsky normal form, and then convert that grammar in Chomsky normal form to a PDA. Then that PDA can't run forever. So if you have a PDA that might run forever, convert it to a grammar, convert that grammar into CNF, and then convert that CNF grammar back to a PDA. That PDA won't actually run forever, which is pretty interesting. Another nice thing about Chomsky normal form. But anyway, Turing machines can definitely run forever. And one thing that we'll see eventually is that we can't even detect if this is occurring. So, but we'll get there eventually. Any other questions about the model itself? Okay, so let's actually make a Turing machine for a language. So here's a language right here. And the reason why I drew the diagram already is that I wasn't going to remember it. So I might as well just do it right here. So this is the language of where the number of zeros here is a power of 2. So is that the perfect squares language? Is it the same thing as 0 to the n squared? This language, which is 0 to the 2 to the n? No. So, for example, like the string with 9 zeros. So that is a perfect square, but it's not a power of 2. Just as an example. So they're not the same. But what do you think we know about this? What can you prove about this language? Forget Turing machines for a second. What can you prove about this language? It's not regular, and you can actually prove also what? It's not context-free. Because of that result, I shared with you that if it's a unary language like this one, then if it's not regular, it's not context-free either. So there's no PDA for this thing. But let's actually try to make a Turing machine for it. So here's the Turing machine, but let's actually try to think about how you would design it. And then we'll see why this Turing machine is the right one. So let's just look at this string right here. So I'm going to have 8 zeros on the tape because it's a sufficiently big example. And then after the input, of course, are all of the blanks, and then it's infinitely far to the right. Okay, so we're to decide, we have this input on the tape right here, and we have to decide whether this input has a length which is a power of 2 or not. If it doesn't have a power of 2, then we should go to what state in the Turing machine? The reject state. If it is a power of 2, what state do we go to? The accept state. If we never go to the accept or reject state, what happens? It runs forever. So we gotta deal with the accept and reject state somehow. But where is the tape head initially pointed? At the very beginning. The leftmost spot, yeah. So it's pointed right here. So let's try to figure out how you would determine whether this thing is a power of 2 or not. Yeah, go ahead. Yeah, I'm gonna go all through the entire diagram, but I want to get the high level intuition of how to actually make this machine first before I show you the machine. So you're to decide whether this input is of length a power of 2. Well, what is characteristic about every single power of 2? What can you do to the number? Divide by 2. And what is guaranteed to happen every single time? Other than 1, obviously. It has 0 remainder, so you can always divide a power of 2 by 2, and you'll get another power of 2. Well, so then for that reason, if we could divide somehow this input into 2 somehow, then perfect, we're all set. Well, how do we divide an input by 2? I could try to shift it, but if I shift the input, like the top half of the input over here somewhere, then I gotta decide whether these two things are a power of 2. So I'm reducing the problem a little bit. But I gotta get down to the base case, obviously. So at some point, I'm gonna have a single 0 here, single 0 here, single 0 here, single 0 here. But isn't that true of all possible lengths? I could do that. So that seems like a worthy strategy, though. But it's fatally flawed for that reason. So we gotta think of a different idea. Well, let's see. Well, what was our idea before when we had the 0s, 1s, and 2s? When we wanted to recognize that language 0 to the n, 1 to the n, 2 to the n. What did we do? No, not with a stack. With a tape. What did we do? Right, so we marked off 1, 0, and then we went through the input and marked off the first unmarked 1, and then kept going, marked off the first unmarked 2, and then scoot our way all the way to the front, and then do another pass, and then another pass, and then another pass. Well, maybe we can try the same idea here. So maybe we can try to mark 0s in some way, and then go back and then do another pass, go back, do another pass, go back and do another pass, and then hopefully we're all set. Well, how do we do this? Well, what is our idea? Because it's a power of 2, we can always divide by 2 no matter what. Well, we can't split the input because of that issue before, but is there a different way that we can split the input?
Mark one off and don't mark the other.
Right. So here's the idea. So I'm going to do it in a different color. We're going to mark one thing off, and then then move right, then skip the next symbol. So the second cell right here, which is currently the first 0, we're going to skip over that for now. Then the next 0, we're going to mark with an X. So every other 0 throughout the entire input is going to be marked with an X. Okay? Well, maybe this idea just doesn't work for powers of 2. Maybe it works for all inputs, the same problem we had before. So maybe let's look at a different input that definitely isn't a power of 2. So maybe let's look at 7 zeros instead of 8, which is not a power of 2, of course. So here are 7 zeros. Well, let's try our marking strategy again. So I mark the first 0 here. Then I mark the 3rd position. Then I mark the 5th position. And then I mark the 7th position. Oh, there seems to be a small difference between these two. What is the difference? If it's odd, then the next 0 that should occur here is actually a blank. So if we have divided a number by 2 and at some point we have something that is odd that's remaining, then what happens is there are obviously an odd number of unmarked zeros. So initially there were 7 here, but of course there are 3 now. There are an odd number of unmarked zeros. Then what will happen is I'm going to mark a 0 at some point, and then searching for the next 0 to skip, I'm going to hit the blanks. And so therefore, we're going to show, for that reason, it couldn't have been a power of 2. Let's actually do an example that is even, but is not a power of 2. Any examples? 6. So let's choose 6 zeros instead of 7 or 8. And here are blanks. So on the first pass, we're definitely going to be okay, because 6 is even, and so we can divide by 2. And so when we mark these first 3, the first 3 X's here, we have a 0 to skip, and then we hit the blanks, so everything is hunky-dory. So then what happens? So we do the going back to the front. There's an issue there. We'll fix it. We go back to the front, and then now we're going to mark these zeros and skip every other 0. Well, what happens is this first 0 right here is going to be, I'll actually do it in a different color. It's going to be marked. Then the 4th position, that 0, is going to be skipped. We're skipping every other 0. But then the next 0, I'm going to mark. But then in searching for the 0, we hit the blanks. And so that proves that the input here, which was 6 zeros, is not a power of 2. But does that show that the powers of 2 work? Well, let's see. Maybe it doesn't work for any input. Maybe we just found that it doesn't work for the non-powers of 2, but maybe it doesn't work for the powers of 2 either. Well, let's go back here. Well, if we're going to mark every other 0, then these 2 are going to be marked on the second pass. And then for the 3rd pass, these other 2 are going to be marked. Oops. These other 2 are going to be marked. And so at some point, because it's a power of 2, we're going to have a tape that is a bunch of X's at the front and then blanks. So then when I'm searching at some point for the first 0 to mark, if I don't find any, therefore it was a power of 2. So this really does work. It does get us the power of 2. Now what is the issue? Oh, unless there's a question.
I think, well, I'm not sure, but on the red ones, the red X's, shouldn't the first X be marked off for 0, and then the second one, it shouldn't be crossed off, and then on the other pass?
You're absolutely right. You're right. Yeah. So, the great point. I went too fast. So the 3rd pass, which is this red one, we skip the other 0, and then we hit blank, so everything's okay there. And then we come back, and then in the 4th iteration, thank you very much, we'll mark the first 0 here. Oh, that's interesting. Yeah. Yeah, so, yeah, that's interesting.
That also was my question. Should one be accepted?
Yeah, it should be accepted. Let's see. So yeah, there's an issue with 1. We'll deal with that and we'll see what happens there. But that should be marked here. Okay, yeah. So there's logic in the machine to handle against 1. So if there's exactly 1 0 here, then what should happen afterward is possibly some x's and then blank immediately after. So if there's exactly 1, then that's a power of 2. Otherwise, if we hit some other 0, some other point, then there's at least 2 zeros left before the marking occurred. So the only possibility here is that there's exactly 1 left, which means that we're going to mark it and then immediately hit a blank after it. Or possibly some x's, but there's no 0 that appears afterward. Thank you for bringing that up.
Well, would that work for the second machine?
It wouldn't work for the second one here because we hit it with 7. So we saw that there were at least 2 zeros along the way. And so we did our marking, but then we were looking for the next 0 and never found it before we hit the blank. Yeah. So So the only way that you could have this problem is when you land at 1, which is only possible if you divided by 2 all the way to hit 1, which means it was a power of 2 to start with. If you hit like 3, 5, or some other odd number, then you're going to see at least 2 zeros no matter what. And so then we'll be able to handle it from there. Other questions? Okay, so let's talk about the machine, because there's actually a lot to get to in the machine itself. So does everyone understand the states? Hopefully we can understand the states. So what is the start state of this machine? Q0, because it has the arrow pointing in. We know this. And where is Q accept? Bottom left. Where's Q reject? We'll get to that. It's not actually on the diagram, so this diagram is not technically complete yet. So we'll fix that though. But the only thing that's left are the transitions. So you may think, okay, what is this transition right here, for example? So if we have a transition of the form A arrow X comma Y, this says if we read an A, write an X, then do action Y. So that's what the notation means. You can think of the arrow as like a transformation of the symbol. So the A is going to be transformed into X by overwriting it with X. And then Y is either going to be L or R, which is to signify which direction to go. And then you may think, okay, so then what about, say, this transition right here, which is not the same thing? So if you see that transition, so a transition of the form A comma Y means is the same thing as writing the exact same symbol down and doing the same action. So if we don't have 3 things on the transition, we must have 2. And on the 2 transitions, we don't really change the symbol that's there. So on that blue circled transition, that says if you see a blank here, write a blank and then move right. Okay? So for the reason why we do that is that most of the time we're not actually changing symbols. There are only certain times when we change 1 symbol or 2 or something. So only a few transitions have all 3 there. So it's just a space saver, really. But you could write blank goes to blank, comma, R. Everyone understand what the transitions mean? Yeah, so the X comma, X to R transition just means if you see an X, write an X and move right.
Also, whatever the statement
Yeah.
is.
Yeah, so if you have two things, the first one is the symbol you read and write. The second thing is the transition, the movement that you do, left to right. Okay, so let's unravel what the machine's actually doing. So let's actually see what the very first transition, in fact, the only transition out of Q0 is doing. So why is it doing that? Whereas all the other transitions are dealing with the X's, the marking. Why is it writing a blank on the very first transition?
Get that first.
It's actually to do with the problem that we had earlier, which is if we're zooming back left, how do we know to stop moving left? We actually don't. So what we do instead is at the very first symbol, the very first cell, we're going to write a blank symbol there. The very first transition. And then when we're going to zoom back to the front, to the left-hand end of the tape, then we're just going to keep going until we see a blank over there. Because we're never going to write a blank where the input is. We're just going to we're going to write a bunch of X's there. We're never going to write blanks. So we can't have an issue of hitting something that we don't want to hit. So we're going to hit the blank symbol at some point, and then after that, then we can make our pass through. So we know to stop moving left at that point. So here we have we're going to have a blank on the front and a blank on the front. And we're going to actually run through an entire computation of this machine on a certain input soon. But let's analyze the machine further. So the very first transition makes sense because as we're going left through the input, going through another pass at some point, we got to hit something to tell us, hey, you're at the very left-hand end of the tape. So what happens afterward? So we're zooming left, then maybe we've marked some things along the way. So at the very left hand of the tape, we have the blank symbol there. Then afterward, we may have marked some stuff, so we may have to see some X's along the way. And then if we see just X's and then the blank symbol after that, what do we know about the input itself? If the entire thing is just X's, if we just keep moving right, no zeros. There's a power 2. So that must mean we need to go to Q except for that reason. So that's exactly what Q1 partially does. So look at the self loop on Q1. It says after we moved right from that the start state here, the very leftmost blank symbol, then we may see X's, possibly 0, but we may see some. We're going to skip past those. And then if you hit a blank, which corresponds in here to go into Q accept, then we accept the input, obviously. So the only possible other case is if there's exactly 1 0 or at least 2 zeros. Because those are the only two possibilities. So let's handle the possibility of 1 0. So there's we see a bunch of X's, and then a 0 somewhere, and then maybe more X's, and then the blanks after that. Well, let's see. So let's look at, the only other transition out of Q1 goes to Q2, which means we saw a 0, and then we marked it with an X and moved right. So look at Q2. We're going to see possibly some X's, so we're going to keep going right until we're going to hit a blank at some point, because there's no other 0. The only 0 was marked, and we saw a bunch of X's. We hit the blank symbol at some point. Well, that's the transition that goes down to Q4. Well, what does Q4 do? Q4 just goes back through the input entirely all the way to the left-hand end, because the only thing on the tape is zeros and X's along the way. So it just goes left until it hits the blank, and then goes right and goes to Q1 as a result. And then now we're at Q1, and there are no zeros left, because we marked the only one there, which is pretty cool. So we handled the case of exactly 1 0. Now let's handle at least 2 zeros. Well, that looks like the Q2, Q3 loopy thing. Well, what happened? Well, look at the transition from Q1 to Q2. We mark the first 0 that we've seen, the very first 0. Well, we marked 1 0, then we must skip the next 0. Well, we may see x's in the middle, so if we mark it a 0, see some x's, which is the self loop on Q2, then we skip a 0, which is the one going down to Q3, and then again we may see some x's along the way, so skip those, and then we got to mark the very next 0, which is the transition back to Q2. And so the cycle continues until, well, hopefully we see a blank after we have marked something, and then we zoom back to the input, to the beginning of the input, and then we have the case from before. Okay, any other questions? Okay, so yeah, so that's the entire machine. So let's actually trace through the machine. So I'm going to actually copy the machine down. And then let's actually see an execution of the machine at work. Hopefully this copies. Copy. Why won't you paste? There. Thank you. Okay, so let's actually look at a particular input that will be accepted. So let's look at 0, 0, 0, 0. And let's actually trace through the computation. So this is the input that's on the tape and a bunch of blanks afterward. Well, what does the very first transition do? It makes the, so actually I should say we're pointed here. So it marks that 0 with a blank and moves right. So at this point, don't think about like, what is the machine actually going to do? Just follow the instructions as the machine would do anyway. So this changes this to a blank symbol with the 3 zeros after and all the blanks after that. And now we're pointed at the second 0. So then what happens? Yeah, so the transition going from Q1 to Q2, changing the 0 to an X and moving right. So then we have blank X because it was just changed. The other two are not changed. And then blanks afterward. And then now we're pointed at the third cell. I'll zoom out a little bit. As you can see, there are going to be quite a few transitions taken here because we're zooming back and forth through the input. Okay, so now what do? We skip it, good. So then we have blank X 0, 0. So the same tape contents as before, but now we're pointed at the next 0. And then now what do? Replace it by an X and move right. So X0X, you should write those in your cards. X0X with maybe another 0. Okay, let's see. So then now what do?
You go left.
Yeah, there's one transition that says blank, move left, and don't change the content there. So what's gonna let's actually just skip a few transitions. So what is gonna happen next? Yeah, it's going to go to all the way to the end, to the left-hand end. So I'm just going to skip a bunch of transitions because purely for the sake of space and time. And we're just going to be pointed at here because the tape contents aren't going to change. So now at this point, we're still in Q4 because we just went left until we hit the blank. Now what do? Yeah, we move to the right because we saw a blank. So we go back up to Q1. So now we're in Q1, pointed at this X, the first X right here. So what transition do we take now? The self loop on Q1, yeah, and move right. So we have the same tape contents, and now we're going to be pointed at the 0 here. And so now what happens? Yeah, I go right and mark with an X, so I have triple X here. And then I'm pointed at this point, and I'm actually going to skip the rest of the computation. So what is going to happen next? So we're going to stay in Q2 for one transition because we're on an X right now. And then the next, because we moved right, we hit a blank. And then Q2 says, go to Q4 and move left. We're going to go back through the input again, hit the blank at the front, and then what's going to happen? It's going to do the Q1 loop over and over and over until we hit the second blank, the one at the 5th position. And then what's going to happen? You're going to go right and move and say accept. Cool. What about a single 0? What's going to happen? It's going to accept it. What about 3 zeros? Well, 2 zeros is going to accept. What about 3 zeros? Well, it's going to mark the first one, so there are 2 left. Then I'm going to mark the first one, skip the first 0, and then move right. But then I'm going to hit a blank. And there's no transition out of Q3 with a blank and then do something with it. Right, there's no transition like that. So what do you think a transition of that form would look like? Or what should it do?
Go to a state that rejects everything.
Yeah, the rejects everything called the reject state. So we can just say, well, at this point, we're not going to really change what's there. We can leave the mess that we made. And so we can just say, blank goes to right, don't change anything, and then go to Q reject as a result. Are there any other states that have incomplete transitions? The start state. What about the start state? Is it missing some transitions? Yeah, it's missing some transitions. What about the accept and reject state themselves? Should we put transitions on those?
Not the accept.
No. So this is actually one of the issues that, about the CSE text, which says that every state must have every transition. It must be fully deterministic. But is there any reason of putting a transition out of Q accept or a Q reject here? No, because if you go there, you're going to stop no matter what and accept or reject, whatever the case may be. So I actually raised this with Michael Sipser. I sent an email to him, and he said, well, it's purely to make the definition easier. But I think it would be more practical to say every state except those 2 states has every transition out of it. So for our sake, we're going to say that every state has every transition out of it except those 2 states, the accept state and the reject state. Okay? But you may see here, well, there could be a lot of states that are missing transitions like this. What if I forget some of them? So you can do this. So you can say something like, all unwritten transitions go to Q reject and move right. Yeah, because these diagrams can kind of get a little cumbersome if you put every transition in. They're fine if you leave them all out. So if you write this, that's fine with me. Yeah, so you have to put the transitions that could eventually lead you to go to Q accept. You have to put those, but you don't have to put the ones that go to Q reject. Yeah.
Will it be assumed that all unwritten goes in there, or will it be at points?
You have to write it yourself. Yeah. Yeah. Think of it like a specification. Like all bad user input goes to this function. So you would have to actually put that in the specification. If you left it out, then you don't know what to do. Yeah.
So these transitions that we're gonna say that they all go to the Q reject, we're saying that we're moving right because we have to move somewhere.
Yeah,
Right?
yeah.
It really matters.
Yeah, because the machine has to be fully deterministic, and we could see the red transition, the one that blank goes to right. We actually encountered that transition when we looked at 3 zeros. So these are very realistic scenarios. Well, the one on Q0, yeah, you're probably not going to see an X there because the input alphabet is just zeros. It doesn't have an X in it. So a transition out of Q0 on input X is very impractical, but we need to be precise about this. So I would just say that because it would cover all possible corner cases. Yeah. And in fact, it's impossible to reason about these machines entirely anyway in the general case. So you might as well just say that to make it easier. So the way that you usually make these machines is you put the path that will lead to the acceptance and then ignore the ones that will possibly go wrong. So here you can just say, well, what if the input really is not a power of 2? What would you do then? Ignore that. Just don't think about it. Just think about the accept case because all of the other transitions go to Q reject anyway. So it's not like a DFA or a PDA where if it's in a certain state that's not final, you have to handle that anyway. Whereas here, if it goes to Q reject, it's going to stop anyway. So you don't even need to think about the bad transitions. Just think about the good ones, which is nice. I think there's
You always have to move left or right on a transition.
Yes. So every transition either moves left one position or right one position. We'll talk about a variation of that pretty soon, but for now it's just left, just right, one position. Yeah.
So for example, would you be like make a machine that only accepts ternary?
Yeah, so a possible question might be, make a Turing machine for 0 to the n, 1 to the n, 2 to the n. So that might be an example. That's actually one that I had on a previous midterm, too. So that could be actually I had 0 to the n, 1 to the 2n, 2 to the 3n. So some number of zeros, then twice as many ones, then 3 times as many 2s. How would you informally do that on a Turing machine? Some number of zeros, twice as many ones, 3 times as many 2s. Mark 1 0, mark 2 1s, mark 3 2s. And then it's the exact same idea as 0 to the n, 1 to the n, 2 to the n. Yep. Other questions? Yeah.
When we draw the diagram, do we need to like put the accept state and the reject state defined?
Oh no. So there's no final notation with a double circle here. It's just a normal state itself, but it's just for computation purposes it's behaved differently. But it's just a normal state. There's no final states here other than Q accept and Q reject. Other questions? Yeah.
So just to make it a simpler diagram for Q0, reading in blank, if we just had all unread transitions go to reject, even if we knew it had to go to reject, we could just write that.
Yeah. So you could do something like, so here you can say blank goes to right and Q reject here. So something like that, that's fine. Yeah. It's never wrong to be more specific than less, but if you write this, you're covered. Other questions? Okay, so let's just say that we were doing this computation again with the 4 zeros, and then we're going through the input, blah, blah, blah. And your friend comes along and says, okay, I'm not sure if you did this correctly. So what happens is he comes during the middle of this execution and wants to verify that it actually did everything correctly. So how would you verify, let's just say at this point right here, that this really is the 5th point in the transition, in the computation. After 4 transitions occurred, this really is the point at which you are. How would you prove that?
Backwards.
Oh, you can run backwards, Or, I mean, you can run forwards, but what would you start from? Well, what is the beginning always? The very first thing before any transitions occur, what happens? Well, what is on the tape? The input with blanks after, and in what state are we? The start state, Q0. And how would you verify, say, that the very first tape contents here would get the second tape contents here? How would you verify that? Yeah, read the transition function. Because then you just say, oh, I'm in Q0 and I see a 0. I see the transition that writes the blank and moves right. And that proves that this is what you get out of it. So let's actually make it a little bit more formal than this. So what are each of these things? So a configuration is a string in gamma star q gamma star. So what in the world am I talking about? Well, is there a way that instead of having like the arrow pointing below a 0 and knowing, we just happen to know what state we're in, is there a way that I can write all of those pieces of information as an actual string itself? Well, writing the contents of the tape is easy. That's no issue because it's literally just the contents of the tape. Well, how do I incorporate where I am on the tape itself as well as what state I'm in? So the way we're going to do this is the state we're in, we're going to write to the left of the place we're looking at. So in this example, where we're pointed at the very left-hand end of the tape in the start state Q0, here we would write Q0 and then the input itself. And this notation says that we're in Q0 and we're looking at the symbol to the right of us. So this says that we're in Q0 looking at the 0 right after where the state name is here. Well, after the first transition, we'll have tape contents that look like this, and then we're in state Q1. So this would be the configuration for the point right after the first transition. So here, remember that the state name occurs to the left of the symbol we're looking at. So in this case, we're looking at the 0 here. So we're keeping track of the contents of the tape as well as where we are in the tape and what state we're in. So I think that's pretty formal. We're getting all the pieces of information really easily in a compact form too. So a computation then is a sequence of configs such that, I should give them names, I guess. A sequence of configs C0, C1, C2, blah, 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 such that, well, every computation must start with the very first configuration, which is the start state, then the input right after it. So here we must have that C0 is what is called the start configuration. So the example before, the Q0 with a bunch of zeros example, that is the start config. And then, of course, the Q1 version is not the start config because it's not the start state followed by the original input itself. And then what must be true about each of the configurations afterward? Well, for the second configuration up here with the Q1, could I have just written anything? Any configuration at all with any state, any tape contents? Or did I have to write a specific kind? Yeah, specific. And the specific means we followed the transition function one step. So what this indicates is that this configuration is yielded, so the keyword here is yielded, from the previous config. So yielded means we have one configuration, we do the transition, and then the resulting configuration is yielded from the previous one. i.e., the first configuration yields the second one. And so, therefore, every configuration yields the next one. So CI yields CI plus 1. It's pretty reasonable.
Do you always have to write the state on top of the input? Because in the previous example, you had 0 and then you write like 0, so you don't really change it. But here we're forced to change an input to a state.
So this has nothing to do with the actual contents of the tape itself. That this is just a string outside of the tape itself. We could carry on with a tape like this, but we want to be able to carry all three of those pieces of information, the tape contents, the state itself, and where we are, all in a single place. So instead of putting an arrow with like the state that we're in right there, this is just a more compact form. It's just it just happens to be a string of this form, but it has nothing to do with the tape itself.
Okay.
Other questions? Okay, I think that's 50 minutes, so let's take a break.
Is that the end of